Hey, good morning. May not be morning where you're at right now, but it's morning right here. And we're going to do our first chapter together. So, this is chapter 7, Gravitation. And some of you guys might have outlined this chapter. It's not that long of a chapter, it's got some weird math in here. And we're just going to talk about it really quick. I outlined a little bit of this chapter myself. I have the homework listed down here, right? And so this will be what's due for this chapter, this homework. And make sure you show your work, right? Show your work. And we should be good. None of the work is too hard. And I'll take you through most of the problems or the types of problems. And it shouldn't be much of a challenge. It's kind of interesting. I know some people are really into space and that kind of thing, so you might really like this. This chapter, we are going to talk about Kepler's. Oops, it's a race. We are going to talk about uh, Kepler's laws, and then also Newton's universal gravitation. And we're going to put those together and kind of change how things work. We're going to be able to calculate the speeds of things orbiting the Earth and the periods, which means the time it takes to get around there. It says also we're going to talk about the importance of Cavendish's experiments. I'll mention that really quick, but it's not really something we're going to dwell on. Okay, so let's go on. Okay, so Johannes Kepler, he took over for Tycho Brahe. And Tycho Brahe was this meticulous astronomer back in the day before they had telescopes and they just looked at the sky. He had all these elaborate measuring devices and he measured where the planets were and where the stars were and how things were moving. And Kepler was his assistant for a while. And when Brahe retired or died, I'm not sure which one, he gave all of his things to Kepler. And Kepler used all that data to kind of formulate how he thought the planets moved. And he used mathematics, which they hadn't really used much mathematics when deciding. Copernicus just said, "Oh, look, they travel in circles," and so Kepler used all this data for 30 years of data and came up with some laws. Now, on my picture right here, this is on Notability, so it doesn't show the graphics like it does. If you'll look on the notes I send you, it's the same notes. Everything's pretty much typed out on it again, but it'll show you the motion here, these things. But his first law says that the paths of things orbiting are in ellipses. And ellipse has two foci, and if you look here, they have two pins in this piece of paper. And we'd be drawing this like this. You stick a string around the two pins and you put your pencil in the middle and then you pull it tight, and when you pull it tight it draws an ellipse, and those 2 points that it's orbiting around there, those are the focuses. Now, foci is plural for focus, so each of those are the ficus. Focus. So in your animation, it works a little bit better. All right. So when you have the planets, and we're talking about the planets, right? So we're using the sun as the center. The sun has to be in one of the focal points, right? And so if you look at this first picture here, the focus, it's a little offside, so this would be oops, it's not showing up very well. I'm gonna do it in yellow, maybe that'll show up. So the other focus may be right there, right? So there's 2 points in the middle, and this right here is really exaggerated, so maybe the other spot would be over here. Okay, and again, this other one's an animation. It shows how they're moving. Now, because of this elliptical shape, the closer the objects are to the sun, or closer they are to the object they're focusing, the faster they go. So if they get around this corner, they're going slow. As they're further away, they get faster and faster and faster, and then they slow back down. And so it's kind of like like on a swing set. When you're at the very bottom, you're going the fastest, and you go up the top, you kind of slow down. Of course, it's going to keep going around in the same direction and not go back and forth like a swing set, but the same kind of idea. Okay, so that's his other. That's the other part of that. The second law or Kepler's second law, is that if you had an imaginary line from the planet to the sun, it would sweep out the same area in the same period of time. So this is per planet. So this is the Earth, or this is Mars, or each one is separate. And so all it's saying is if it's the same time period, it will sweep out the same amount of space. I don't know if you can tell what I'm doing there. I just kind of colored that in. And so these two areas are the same size, different shape, right? Well, they're kind of like triangles. I don't know what you'd call that, an arcish triangle, but they're the same area. It took the same amount of time to make that. So that helps get the speed. See, it's not traveling as far. It's not traveling as far on the axis here. It's not traveling as far because the area in there is further away. It's a bigger area per littler arc. Here it has a larger arc, so it has to go faster during that spot to cover the same amount of space. Now, again, if you go onto the Google Notes, it'll show you a nice little animation, and that's right here. It's frozen on this. I don't know if there's a way for me to do that. Maybe I'll tap on it and see what happens. No, so nothing happens. All right, and that's just another way, another way to measure the speeds mathematically. All right. Kepler's third law, and this is what the problems are going to be on, the first set of problems. Kepler's third law is just talking about the relationship between the time period, right, and that's that same little graph, right, time period, and then the distance that they are from the planet in general, okay? So it's talking about those two things. So the T stands for the period of the planet. So maybe the period of the Earth around the sun is 1 year, right, for us, or 365 days, right? That's one period. So that's the time period. That's how long it takes to get around it. And then if you have another planet going around the sun, we'll say Mars. I don't know what the period for Mars is, but when you're relating those two things, r is the distance. Let me see if I can change the size of this here. R is the distance from the planet. We'll call that R Earth. And this is Mars here. Oops, that's a little crooked. We'll call that R Mars, right? So that's the radius, is the distance from the central focus. All right. And then the T of Earth, would be 1 year or 365 days, whichever you want to do. And then we could calculate the time that it took Mars to go around the sun also. All right, very convenient to see how long how far these planets are away from the Earth. If you know how long it takes it to get around, you can find the distance, or vice versa. Okay, let's solve this problem. All right. So if we read through this information, if Ganymede, one of Jupiter's moons, has an orbital period of 7.15 days, how many units are there in its orbital radius? Use the information in example problem 1. Well, example problem 1, I went back and I wrote down that information on the side here. So if we'll look at this is talking about Io. Io's moons, right? Or Io, the moon around Jupiter. So the period of Io is 1.8 days. The radius, the radial units, that's the distance it is from Jupiter, is 4.2 units. And then on our problem, it says we have 7.15 days. And that's our period of moon G. All right? And then we're going to try to solve for the distance in radial units away from Jupiter for G. Okay, now, Okay, come on, let's go. Now what I want to do here is I want to solve for RG. So I'm going to put RG on the top of my equation. Now if we look at our equations we had before, our equation is TA over TB squared equals RA over RB cubed. All right, so I'm going to start with what I'm trying to solve. I'm going to solve RG, so I want that on top of my fraction. So RG cubed, right? That's the R is cubed, over RI cubed. So I put the G on top because I'm solving for G. Now when I put in the periods, I want to just make sure that I have them in the same orientation. So the period of G squared has to go on top, and the period of IO squared has to go on the bottom. See how I have that set up? Now I'm going to do my algebra right now. So what I'm going to do is a little cross multiplication. I know you can't do this like this on your paper, but I'm going to lasso this R, and I'm going to move him through the equal sign and cross over to the top. I'm going to put a 1 down there just because it really belongs there, but just because, okay? And now we're set up in the equation. All right, so let's sub in some numbers. So TG squared, 7.15 squared times RI cubed, 4.2 cubed, divided by TI squared, 1.8 squared. All right, now that's going to be equal to RG cubed. So we have to be careful when we're not done once we find this answer. We have to take the cube root of this. Okay. I have to get my calculator started, and I have 50 people texting me. All right. So I'm punching this into my calculator. I should do this on the video so you can see it on here, but then I can't see my problem. So I'm putting in 7.15 squared times 4.2 cubed divided by 1.8 squared equals. Now that equals like 1,169. So if you have that on your calculator, that's what I have. That's good. Now we're going to push the cubed root. And I end up with 10.53 units. And look, does that make sense? Now it's a lot farther away. It's over twice as far away, and it takes longer to get around. And that does make sense to me. Okay? And that's kind of how these problems work. All right? Now I want you to try the next 3 problems. Before we do that, let's look at this. An asteroid revolves around the sun, which is a mean orbital radius of twice that of the Earth. Twice that of the Earth. Okay, what I'm going to do is I'm going to write these givens out for this next one for you. I won't do the problem. I'll just write out the givens. And we can have a little shortcut we can take. So it says that its radius is twice the Earth. So let's call this RE. That'll be the radius of the Earth. We'll call that 1. Our asteroid is twice as much. Call that 2. There you go. Now you could have used your numbers from this chart down here, and you're going to get the same answer, but why make it harder when we can use easy numbers? Okay, now this is going to be in Earth years, right? Predict the period of the asteroid in Earth years. Okay, so TE, it takes 1 year to get around the sun. And then we'll say TA is what we don't know, and we'll solve for that. Okay. you want to put TA on top of the fraction, right? It looks like I'm solving the whole thing. I'm just going to do this first part. So TA squared over TE squared equals RA cubed, right? A's and A's on top, RE cubed, all right? And so what I want to do is I want to get that TA by itself. I've already put it on top. I did that on purpose because that makes it easier. Now I'm going to take this, lasso it, pull it up here, throw a 1 down there to make the math teachers happy, kaboom, and there's your equation you can use. All right, I hope that helps. All these other problems are very similar. They're using other distances and days. It doesn't make a difference what units they're using. All you have to do is make sure you use that equation in the right way. Make sure what you're trying to solve you're putting on top, and make sure that you take your cubed root or your square root after you find that answer, and it should work out very fine. Okay, so that's what we're going to call today's assignment. Just finish those problems up. I will have an answer key that you can check your answers out, and I'll post that. I do not have my teacher's edition here at home right now, so I'll have to run to school, and I didn't even think about that till just now. So as we go along now, if you want to work ahead, which is fine, the next section of this is all laid out for you in the notes, and you have the Google Notes, right? And we're just going to go through there. In our next section, which we'll go over in our next video, which will be maybe tomorrow or the next day, and we're going to do practice problems 12, 13, and 14. And then we're also going to finish that chapter up, and I put some review problems there at the end. Okay, so the chapter is gravitation, the chapter's homework is all listed there if you want to work ahead. This will be week number 4's assignment. So once this chapter is finished, this will be what's your score for week 4. Next week then we'll go on and we will do a new chapter. I hope this makes sense. Again, I'll come back and I'll finish this lecture on another video later this week, and probably on Thursday. I'm alternating chemistry and physics, and so probably on Thursday, but if you do want to work ahead, you may. And all you have to do is take a picture of your homework, show your work, and just send that to me. And be safe out there and practice social distancing. I'm outside right now, and I'm enjoying this wonderful weather. A little bit rainy. I've been working outside. Let's see if we can get a video here. I don't even know how to do it. I'm really good with this machine. Oops. Hey, there we are. And so I'm out in the old Walnut Grove. Hoping you guys have have no problems with this section. And if you do, just give me a remind, and I'll try to help you out as best I can. Hey, have a great day. Thank you.